So in this video, I'll talk about the proof of John's theorem. In the last video, we saw what John's theorem was. So let me recall that we are in the n-dimensional Euclidean space equipped with the Euclidean norm, and John's theorem basically said that given a convex body K, the following statements are equivalent. And what are they? They are statement 1 that Vn is the max volume ellipsoid of K. So this is Bn, which is the unit wall, is the maximum volume ellipsoid contained in K, which we will denote with this abbreviation max wall ellipsoid. And the second statement is that Bn is contained in K, and there exists U1 to Um belongs to the boundary of K intersection the boundary of the unit wall, and M non-negative real numbers such that A summation I equals to 1 to M, Ciuy is equals 0, and B summation I equals to 1 to M, Ciuy Ui transpose equals to In. This is the theorem statement, and we saw what it means. Basically, now I will give you a proof. Before giving you the proof, let me make a small point here. So we'll do the proof for the symmetric convex body, because proof for the non-symmetric convex body requires a bit more algebra, and that is given in the lecture notes. So I have wrote out the proof for the general case as well, but in this video I'll just cover the symmetric case. If you are interested, you can have a look at the lecture notes. So in the symmetric body case, the first thing to note is that like a symmetric convex body is defined as the convex body for which if x belongs to the convex body, then minus x also belongs to the convex body. So in the symmetric case, if you have that your ui is a contact point, right? And note that the volume, the unit ball is also symmetric, right? So if ui and your convex body is k and volume, the ball is the bn, both are symmetric, then if ui belongs to the intersection of boundary of the convex body delta k intersection delta bn, right, then minus ui also belongs to the intersection of the boundary of the ball and the convex body. And that's basically, I mean, basically by the fact that if u belongs to k, then minus u also belongs to k, particularly if ui belongs to delta k, then minus ui also belongs to minus delta k, and ui belongs to bn also implies minus ui belongs to bn. So both u and minus u will lie on the contact point, set of contact points between the ball and the convex body. So what this specifically says is that, let me write it as a side note, that if k is symmetric, then ui and minus ui are both contact points, right? And this implies that if I say in the John's theorem, right, we had summation Ciui equals to 0. So here we will end up having some Ci for ui and some C dash I for minus ui, right? And we have rest of the things. J not equals to I, j equals to 1 to m, ci ui, sorry, cj uj equals to 0. So note that now what I can do is I can make this ci as ci plus c dash I by 2 times u, and uh, yeah, one second. Yeah. No, so essentially what the thing is that if only ci was in the summation, right? And say minus ui was not in the summation, then I can introduce minus ui here, right? By doing this. So ci by 2. So I'll put ci by 2 for ui and and ci by 2 for minus ui, right? So then this will ensure that this summation is equals to 0. So therefore, by changing the now changing the choice of C, we can essentially end up having one less term in the summation CIUI. And therefore, uh, basically we can reduce all the reduce the summand on the left hand side. Like so we can bring this quantity to be an empty summation. Basically by doing this operation that we will keep choosing CI such that we will place the mass uh, Ci on ui and Ci on minus ui so that they add up to 0. And note that this second condition does not change because again we have Ci by 2 ui transpose plus Ci by 2 minus ui transpose, and this thing is actually Ci ui transpose. So basically what we can do is without hurting the second condition, we can make this condition trivial. So we can ensure that this summation is empty and therefore this condition becomes trivial, but this condition still stays non-trivial. So, and you can do this only if the body is symmetric. So for the symmetric case, it suffices just to prove this condition, right? I mean, this condition does not add any value to us. So we will focus on showing that if Bn is the maximum volume ellipsoid, then this holds. And if this holds, then Bn is the maximum volume ellipsoid. And we will start with the easier side, which is 2 implies 1. And this was proven by Keith Ball. And I mean, this is not, so 2 implies 1 is not actually the content of John's theorem in the original paper. But later on, Keith Ball showed that this direction also holds. John initially just proved 1 implies 2. Anyway, this is the easier direction, and so we start by writing this. So suppose, so we know that Bn is inside K, but suppose that there is some other ellipsoid, T times Bn, where T is some PD matrix, right? This is another ellipsoid. So suppose this is the bigger, so this is an ellipsoid of even bigger volume than Bn. Suppose volume of Bn is greater than volume of Bn, right? So this basically implies that determinant of T is greater than 1. Now note that why should we consider only ellipsoids that look like TBN? Like why shouldn't we add a translation parameter B? So the general ellipsoid is this B plus T of Bn. But here we are just considering T of Bn because note that the convex body is symmetric, so if we have the ellipsoid at a position which is not at the center, so whose center is not at the origin, then in that case the volume cannot be maximum. Like you can show with some small argument that essentially say your body is like this and this is your origin. So you can show that if an ellipsoid has the center somewhere other than the origin, that cannot have the maximum value volume. Like, I mean, if you bring this to the origin, and then you can see that like this ellipsoid can now even be extended further, right? Yeah. So it suffices to uh, basically look at ellipsoids of this form, which does not have a whose center is basically at the origin. So now, by our assumption, we have the determinant of t is strictly greater than 1. But what we know is that we are given condition 2, right? So condition 2 says that the contact points between the ball and the convex body satisfy this. So let's see what happens for the thing. Yeah. So we have I equals to 1 to m ci ui transpose equals to in, right? Now let's look at this quantity t inner product in, which we will define as summation I equals to 1 to n, j equals to 1 to n, t of ij times, I mean, let me just define this for a general matrix. Yes, Sij, right? And these are the individual entries of the matrix T and S. So here Ts belongs to R n cross n. So we will use this notation, right? And with this notation, the interesting fact is that T of in is nothing but the trace of T. Why is this the case? Because when S is equals to in, here everything is 0 except the component ii, right? Which is 1. So only the ii terms survive, and that is exactly equals to the trace of the matrix. So in some sense, basically you are taking an inner product of the two matrices where you write the first matrix as a very long vector with n square entries, and you write the second matrix as another long vector with n square entries, and then you take an inner product on them. So, but I mean, this notation will come in handy in manipulating our algebraic quantities. So this is what we have. So let's look at what is the inner product of this quantity. This we know from equality that this is trace of t, which is fine. And what happens to this quantity? This actually again by a clever manipulation, we can show that this is first. I mean, just by the linearity, first we can show that this is equals to Ei times inner product of T of ui transpose. Right? This is equals to trace of T. And this inner product is again like by using some algebra and this definition, we can show that this is nothing but we have trace of T here is nothing but Ci into ui, right? This is the quadratic form ui transpose T times ui. Yeah. And now what we have is this equality. Now what can we say about the values of this whole thing? Now again, yeah. So note that this ellipsoid is uh, we are looking at ellipsoids that are contained in the set K, right? And therefore, in the previous lecture, we saw something like the following, that if this is the surface of your convex body and this is the delta Pn, then the hyperplane at this point ui, that basically is the supporting hyperplane, that is same for both delta k, for k and bn. So basically, and that hyperplane was given as ui comma x less than equals to 1. I mean, the hyperplane was given with equality, and we saw that k lies, so k is a subset of all x in Rn such that this happens. So basically, now if particularly if we want that Tbn is a subset of this, right? So then it means that so let's look at ui also belongs to Bn, right? Because ui lies on the boundary of Bn. So what happens to T of ui, right? That has to satisfy this. So this means T of ui inner product ui is less than equals to 1, which is same as y T ui less than equals to 1. So what we have is trace of T is less than equals to summation I equals to 1 to m pi. And last time we saw that this summation is equals to n. So therefore, we have that the trace of T must be less than equals to n. And now note that this trace of T is nothing but trace of T is the sum of eigenvalues of T, right? And we know that sum by AMGM inequality. So this is greater than, so let's write it this way, by n greater than equals to product of the eigenvalues to the power 1 by n, right? And this is nothing but the determinant of t power 1 by n. And further, we had that we just showed that the trace is less than equals to n. So this is less than equals to 1. So we have determinant of t less than equals to. So basically, this is a contradiction. So it's basically showing that any ellipsoid Dbn that is contained in K must have determinant at most 1. And we know that Bn is contained in K, right? So volume of Tbn is definitely less than volume of Bn, and therefore Bn is the max volume ellipsoid. So this concludes the proof in the implication 221.